explained in the previous video, errors in quantum computation are classified into three kinds: state preparation error, gate error, or measurement errors. And my current research focuses on state preparation and measurement errors, that is, span. The most widely used methods for correcting span is transition matrix correction, which measures the overlap square matrix between our initial and final classical states, and use this information to classically correct subsequently measured data. Each element of this transition matrix is a probability we measured after preparing a noisy classical state, 0 or 1, and measured in computation basis, with an empty circuit in between. It characterizes what we measured after intending to prepare a certain classical state. If there is no span error, the transition matrix is an identity matrix. Each column of this matrix corresponding to an input state, sums to be 1. Each row is a measured state. We denote this transition matrix as T matrix. E is multi-qubit POVM. It is noisy. Rho is a noisy classical state. According to the definition of T matrix, we can get back the ideal probability distribution while inverting this equation. This method has been widely used in experiments. However, there are several limitations of this approach. First, the complete implementation requires 2 to the n probability measurement, which is not scalable. The classical processing of the calibration data is also inefficient. Besides, the transition matrix may become singular for large n, preventing direct inversion. Third, the inverted transition matrix might not be a stochastic matrix. That is, it can produce negative corrected probabilities, and the correction is not rigorously justified, so we cannot be sure that we are only removing span errors and not corrupting an estimated probability distribution. This work focuses on the first 2 problems. The key to these problems is approximating multi-qubit transition matrix with a tensor product of single-qubit transition matrices, and we assume qubit mainly interact pairwise. The tensor product structure and locality are essential to scalability. However, it may not be immediately apparent based on this definition, and they are not rigorously presented without an additional assumption. In short, we want to associate an idealized non-interacting qubit model with a real interacting qubit system, while a complete positive trace-preserving map. That is, to each physical system or device, we introduce an associated non-interacting qubit array consisting of a register of n qubits, each coupled to its own measurement apparatus, but with no cross-coupling between qubits or detectors. We assume they are all independent with each other for now. A key assumption is that states of interacting and non-interacting systems are related by a completely positive trace-preserving map. Here, nominal is a completely positive trace-preserving superoperator. A sufficient condition for this assumption to hold is that the ground and excited state of the coupled qubit can be obtained by adiabatically turning on the qubit-qubit interaction. However, we don't require this map to be adiabatic or even unitary, but we exclude cases where the initial state of uncoupled qubits entangled with the environment, and cases where turning on the qubit-qubit coupling caused leakage out of the register. In these cases, the map would not be complete positive trace preserving. If the qubits are uncoupled, multi-qubit POVM are tensor products of the single-qubit POVMs. Namely, the non-ideal multi-qubit classical state is separable and can be written as tensor product of single-qubit density matrix. Here, these E are 2 outcome POVMs for each single qubit because they are noisy, non-ideal. They differ from projector and may vary from qubit to qubit, but the multi-qubit measurement operator are tensor products of the single-qubit ones. The single-qubit transition matrix obviously depends on the initial classical states of that very qubit. However, it actually also depends on the entire initial state, the n-qubit register. This dependence is relatively small compared to the former one. So there is a leading part, which is a mean, and a fluctuation. It would be really easy if we could ignore the fluctuation. But the fact is, it's not small enough to be ignored, especially as the register size increase, the discrepancy accumulate. We will talk about this later, but let's start with a little bit math. If we substitute this equation to a formal equation for transition matrix, we have, and we can expand this in power of fluctuation. The zero order one is the easy part we just talked about. It means the approximation without crosstalk, without the interacting map. As for the first order approximation, together with a formal definition, it seems that it vanished. Is that really just a zero? I'll put it as zero for now. The second order is a pale correlation, and the third order is a triple correlation. Our intuition is, as the order gets higher, the effect should be smaller, and the data we measured from real quantum computer agree with this. Actually, the third order approximation is already small for many cases. Another question comes to mind. Here, we just have some math and build upon some assumption. But a quantum computer is a physical device. What should the reality be? Will a pair of qubits that are physically located close by correlate in a similar way as those are far apart? More importantly, are those assumptions valid? We keep a question in mind. Let's look at some data. We mainly check this: overall magnitude of span error, overall correlation error, pale correlation, and higher order correlation like triple correlation. We investigate a chain on a 14-qubit device first. Another chain, a chain that is more separated, and a two-dimension square in the same device. Wow! Go back to a chain. We check on another 5-qubit device from IBM. We also take a look at Rigetti device. Note that the last two devices have retired. They have better device now, and we did notice that for the Rigetti device, qubit 4 is a bad qubit. It is consistently bad while we took those data. So with this data, it seems that pale correlation model is reasonable on linear array of qubits, but may not necessarily work for other cases. Qubits that are more closely separated or with two-dimension geometries may show more complicated span error correlation. As for these cases, we did check the third order. However, adding the third order didn't really help much. That means these cases beyond our current model. With this data and those pending questions in mind, we have to go back to check our work. We think that the main problem is that the first order approximation does not vanish, especially if we check the Rigetti case. After we introduce that bad qubit, it messes up everything. To study the first order approximation, we need to check the spectator qubit much more closely. When we say spectator qubit, we mean other qubit in that register. For example, in these cases, a register is qubit 0 to 3. And when we get single qubit transition matrix for qubit 0, qubit 1, 2, 3, these three qubits are spectator qubit for qubit 0. The state of these three spectator qubits have an effect on qubit 0. This effect could not be ignored. We had more works and data for the problem related to spectator qubits. We could finally reconstruct the transition matrix, even for large register size, but with higher pay. We also improve on qualifying error. I'd like to end this video here. But before I end, I do want to point out some assumptions in these videos are invalid, and some procedures may not be very good. At least for some cases, it's bad, but our data made us admit that. However, we are not saying that transition matrix or the methods we explain here is totally useless. I guess it depends on your application and tolerance for errors. We had much more work on spam, both on transition matrix and another new method, quasi-probability decomposition. It seems that for better correction, you just have to pay more. So, which method is better?